Hello again, this is Paul Watts here from High Flying Physics, supporting students aiming for top grades. This is another short video that aims to stretch and challenge A-level physics students. And this one in particular looks at circular motion, but in a slightly more unusual context, which sometimes flummoxes some students. We're imagining being on a train, and attached to the ceiling of the train there is a piece of string with a mass hanging freely at the end of it. As the train rounds a bend, the pendulum appears to deflect off to one side, and this question looks at the physics behind that. But before we dive in, please make sure you subscribe below, or like or follow, depending on whatever platform you're watching this video on, and just to make sure that you receive all the more video gems like this. Also, make sure you log on to www.highflyingphysics.co.uk to get access to the longer based topic courses when they become available. Okay, let's have a look at this question then. Okay, a train rounds a bend at a speed of 48 meters per second. On the train, a mass of 0.25 kilograms suspended by a length of string is deflected sideways by an angle of 15 degrees. And the question is, calculate the radius of the bend. As with all these types of questions, we first of all draw on the forces which are acting on the mass. First, we've got our weight. We've got our tension acting up the string. So the first question we need to ask ourselves is, why does the ball deflect? Well, as the train turns the corner, the ball tends to keep moving in a straight line. And we know that from Newton's first law of motion. Newton's first law of motion, as you all know, all things continue in a straight line at a constant speed unless an external force acts. As the train takes the corner, the ball wants to continue in a straight line. So that's why there's a deflection. Now, it's the horizontal component of the tension, and I've drawn that there in green on the diagram. Hope you can see that. It's the horizontal component of the tension that pulls the mass away from the straight line path into the circular path. Hence, overall, the tension in the string increases compared to the situation when the train is moving in a straight line. And it's this horizontal component of the tension that is the unbalanced force, and that provides the centripetal force. We can redraw the diagram in the form of a vector diagram. And when we do that, as you know, we put our vectors head to tail. So we start off there with weight, and then we can add our tension. And then we notice that the start of the tension and the end of the weight, there's a gap. And that gap represents the resultant force, and that's the centripetal force. So that is the unbalanced force. So let's go back to the question, and what we're trying to do is to calculate the radius of the bend. So the first job here, we need to work out the vertical and horizontal components of the tension. We know the tension is 15 degrees from the vertical, so if we draw on our vertical component of the tension, that is T cos 15. Horizontally, in the green line, T sine 15. Now, we can resolve the forces vertically, and what we can say here is that the forces acting downwards are equal to the forces acting upwards. And we know those two forces must balance, because as the train rounds the bend, that mass is neither accelerating upwards or downwards. So W is equal to T cos 15. Working our way through that and reorganizing that formula, we can say T is equal to W over cos 15, substituting mg for W, putting in 0.25 kilograms and gravity 9.81. Our tension is 2.54 newtons. Now we can resolve horizontally. Now the thing is with resolving horizontally is that we've got an unbalanced force here. The force acting off to the left there, the horizontal component of the force, T sine 15, is going to be providing the centripetal force, the unbalanced force. So we can say t sine 15, and substituting our value for t, which is 2.54 times sine 15, is equal to mv squared over r, the formula for centripetal force. And then we can say 0.68 is equal to mv squared over r, and working our way through there, we can see that the radius is equal to 847 meters. So there we go then. That's actually a fairly basic question in circular motion, but in the context of the pendulum, it sometimes sort of muddles students. Just as an aside, it's always a good idea after you've watched a video like this, just to go back to it, maybe 2 or 3 days later. Go back to the question that's been asked and see whether you can answer it by yourself. Good. I hope that's been of help to you, and we'll see you soon. Thanks. Bye.